Hello everyone, so this is the GCSE Combined Science Trilogy walkthrough for Chemistry Paper 2. This is the foundation tier paper that pupils sat in June 2019. I'm going to go through and model how I would have tackled it. I've attached in the description a link to the blank past paper and the mark scheme, along with revision videos question by question if you need to go back and revise the content. So, starting with question number 1 then. This question is about gases. Draw one line from each substance to the description of the substance. So we've got air, carbon dioxide and oxygen, and you've got element, compound, hydrocarbon, metal and mixture. So you process of elimination straight away. None of these are a metal, okay, obviously they're all gases, so they are not metals. And then that's eliminated one of them. Now, oxygen is an element because we find it on the periodic table of elements. Carbon dioxide is CO2, which means we've got carbon and oxygen bonded together, so therefore that makes it a compound. And air is loads of different gases. You've got oxygen floating about, you've got argon floating about, carbon dioxide, nitrogen, all floating about, but they're not bonded to each other, so therefore it makes it a mixture. Question 1.2. What is used to test for each of the gases? So this is some chemical tests you just need to know. Oxygen, the test for oxygen is that it relights a glowing splint. Okay, so if you put a glowing splint into oxygen, it will relight. For carbon dioxide, we use lime water. Lime water is a clear solution, but if we put carbon dioxide into it, it goes cloudy. A lighted splint is what we test for hydrogen, and that is what gives us the squeaky pop. And then litmus paper is the test we use for chlorine. And chlorine, just like it does if bleach gets onto your clothes, it bleaches the litmus paper white. So those are the 4 different gas tests that you need to know. Question 1.3. Give 2 reasons why the percentage of carbon dioxide in the air has decreased in the last 2.7 billion years. Well, combustion, that is the process of burning fossil fuels, so that would release it, so it's not that. Intense volcanic activity, well, that would again release carbon dioxide, so it's not that. And respiration, the process of our body getting energy. We breathe out carbon dioxide because respiration makes carbon dioxide, so it's not that. So that leaves us with dissolved in the oceans and photosynthesis. Oxygen reacts with sulfur dioxide. The reaction is reversible. What is the symbol for a reversible reaction? Well, the symbol for a reversible reaction is this one with 2 half arrows. Remember, in pretty much 99% of chemical reactions, it's permanent, so we just use an arrow, but for a reversible reaction, we use 2 half arrows. So complete the sentence then. In a reversible reaction, the forward reaction is exothermic, so the reverse reaction therefore must be the opposite of an exothermic, which is endothermic. So just using a bit of logic there. A reversible reaction happens in apparatus which stops the escape of reactants and products. Complete the sentence. Equilibrium is reached when the forward and reverse reactions happen at exactly the same, and your answer should be rate. Okay, so you can say that when the forward and the reverse reactions are happening at the same speed, we say that they are happening at the same rate, because they would be at equilibrium, which means things are balanced. Question 2 then. Concrete contains cement, water, sand and small stones. Concrete is a mixture designed as a useful product. What do we call a mixture that is designed to be a useful product? Well, finite means that the resource will run out, so it's not that. A formula, well, that is like a chemical formula, like CO2, so it's not that. And a fraction, that is to do with a part of crude oil and different length hydrocarbon chains, so it's not that. So a formulation is the name that we give to a mixture which has been designed to be a useful product. Another example of a formulation is paint. You've got to have the right components in paint and to designed measured quantities to make the paint effective. You've got to have the right binder, an amount of binder to make sure it gets to the walls. You've got to have the right amount of solvent to make sure it's not too thick or thin. And you've got to have enough pigment to give the colour that you want. So we would say paint is also a formulation. Concrete contains cement. Cement is made by heating a mixture containing silicon dioxide, SiO2. Why does silicon dioxide have a very high melting point? Tick 2 boxes. So this is actually linking in a part of chemistry paper 1 knowledge. So just because you've sat chemistry paper 1 doesn't mean that they can't ask about some of the stuff in chemistry paper 1 in chemistry paper 2. So silicon dioxide then, we should remember, is one of the giant covalent structures, a bit like diamond. Okay, so what properties do giant covalent compounds have? Well, they are giant structures. They are hundreds of molecules big. So therefore it's not number 2. A simple molecular structure would just have a couple of atoms. It is a covalent structure, so therefore I would think it would have strong covalent bonds. It's not an ionic structure, so it's not ionic bonds, and it wouldn't have weak intermolecular forces. It would have strong covalent bonds between it. So it would be the first and the third option. Student A investigated how the mass of the small stones in concrete affects the strength of a concrete beam. All other variables were kept the same. So they were changing the amount of small stones in it. Draw one line. The student then added weights until the concrete beam broke. Figure 1 shows the apparatus they used. So they have their concrete, they're adding masses to it until it snaps. Draw one line from each type of variable to the correct example of the variable. So we should remember independent is what we change and controls are what we keep the same. Just for reference, the dependent variable is what we measure or record in our tables. So what are we changing in this practical? Well, it said it in the question here, we're changing the mass of the small stones. So the independent variable would go there. What should we keep the same? Well, if it's something that's going to affect the practical, it would be the length of the concrete beam, because it's told us everything else has been kept the same. And just for reference again, the dependent variable, what they are measuring is how much weight is needed to break the beam. Okay, the time taken to add the weights, not actually needed. Okay, so that one there is just put there to confuse you. Table 1 shows student A's results. You need to plot the data from table 1 onto figure 2. The first 3 points have been plotted for you. You then need to draw the line of best fit. So again, we just need to make sure our plotting is really accurate here to get 2 marks, and the third mark would be the line of best fit. So we can see that 500 grams, that one's done. 1,000 grams, that one's done. 1,500, that one is done. So at 2,000, the weight needed was 100. So we can go 2,000 straight to 100. 2,250, which would be halfway between 2,500 and 2000 is 85. So you would go up halfway between 50 and 100 is 75. So each little square is worth 5, and you would go up 2. So therefore, 85 would be placed there, 2 squares above 75. 2,500 would be 65, which would be 3 lots of 5, so 3 squares above 50. And then 2,750 would be 35. Okay, so that halfway between is 25, so 2 squares above it would be there. I would then continue my line of best fit, so I can see it goes up, it then decreases. So as long as you've got a kind of accurate curve following the data, you'd get the mark for that. Question 2.5. What mass of small stones would be needed to make the strongest concrete? Give a reason for your answer. Use figure 2, so we can go back to our graph and we can see what is the mass of stones that gives us the highest weight. Well, we can go across from our highest weight down, so it should be 1,500. Okay. Why did we select that number? Well, it's simply the highest point on the graph, or you could say it needs the biggest force to break the concrete. Student B did a similar investigation. Figure 3 shows student B's results. How could student B improve their investigation? Use figure 2 and figure 3. It's only 1 mark, but we can see what's different about graph 2 and graph 3 is that graph 3 has only actually done 2 experiments. He hasn't done many different masses or different amounts of stones. So what he needs to use is use a greater range of values for the independent variable. Okay, or you could just simply say take more measurements. But the key thing is he should do more numbers to give him a better pattern. You can't get a pattern just from 2 results. Question number 3 then. The student investigated a rate of reaction between magnesium and hydrochloric acid, and it shows the apparatus below, and you're using a gas syringe. So you're measuring how much gas is being made from the reaction. It then says balance the equation for the reaction. It's only 1 mark, and they've given you 1 blank space. So we can see that on the left-hand side of the equation, we've got 1 chlorine. On the right-hand side, we've got 2 chlorines. So therefore, the easiest thing to do is just put a 2 there, and that means our chlorines are then balanced. So we'd have 2 chlorines on the left and 2 chlorines on the right. And then that automatically balances our hydrogens as well. So that just solves it all. The student used 50 centimetre cubed of hydrochloric acid. Which apparatus would measure 50 centimetre cubed of hydrochloric acid with the greatest accuracy? Well, this is effectively saying, what device do we use to measure volume? Beakers and conical flasks, which are these triangular flasks, do not measure volume accurately. They are very rough instruments. We should use a measuring cylinder because it has the highest resolution. You can break it down on a measuring cylinder down to millilitres to make sure that you're getting the right amount that you need. The student measured the volume of gas every 20 seconds for 2 minutes. The volume of gas was 0 at the start of the experiment. The measured volumes of gases were, and they're listed there. It says complete table 2 to show the results. So we now need to design our table. What goes at the top of our table? Well, it's our headings. We are changing the time in seconds. Okay, we are in control of that, and it said they're changing it every 20 seconds for 2 minutes. So we're just going to go up in 20s, 20, 40, 60, 80, 100, 120, 120 seconds in 2 minutes. We would then have our volume of gas. This is what we're recording in centimetre cubed. Now, what order is it going to go up in? Well, you can't lose gas from a gas syringe. It only goes up. So you start with the smallest one and work your way up. So just do it carefully, one at a time. So I can see 26 is my smallest, and then cross it off. Then it would be 38, and 47. Well, actually, you can see it's made it easy. It's going up in order. So 59, and then 60. So you'd get 1 mark for each for your headings, and then 1 mark each for substituting in your values to give you the 4 marks. Some of the volumes of gases were lower than expected. Suggest a reason why. Well, it's possible that in the experiment, maybe they didn't add the right amount of acid. Okay, so there might have been less acid. They might have used a lower concentration of acid. Okay, they might have used slightly less magnesium, or the time that they take might have been slightly different. They might have been off with their timings. The student then repeated the experiment using different concentrations of hydrochloric acid. So they are now changing how concentrated the acid is. So give 2 variables that they should keep the same. Well, if they're changing the concentration of acid, they then need to keep the other variables the same, like the length of magnesium, or the amount of magnesium, or you could say the mass of it. Then you also, although you're changing the concentration of the acid, you would keep the volume of acid the same. And another one you could say is the temperature of the solution. Because you should know if you've got a higher temperature, you'll have a higher rate of reaction. Question 3.6. As the concentration of hydrochloric acid increased, the rate of reaction, so we're using our common sense here, if you increase the concentration, the rate of reaction would also increase. This is because there were more acid blank in each cubic centimetre. Or if you've got a higher concentration, you would have more acid particles in that given volume. So therefore the collisions happen more often or frequently. Okay, so this is your basic kinetic theory of reactions. If you don't remember that, make sure you go back and watch the revision video for it. Okay, so question number 4 then. Large hydrocarbon molecules can be cracked to produce smaller, more useful molecules. Alkanes and alkenes are produced when hydrocarbons are cracked. Give 2 conditions that are used for cracking. Well, to crack something, we want to break it into smaller pieces, so we heat it up, so we use a high temperature. That's why we use a Bunsen burner to do it. And we could also use a catalyst to reduce the amount of energy we actually need to put in. And we could use steam or a ceramic catalyst. Butane, C4H10, is an alkane. Figure 5 shows part of the displayed structural formula of butane. Complete the displayed structural formula in figure 5. So it's told you the molecular formula there, C4H10. So we now need to make sure that we write it out in its structural formula. So the first things I will do is add my carbons on to make sure I've got my 4 carbons. And then I've got to make sure I add my hydrogens on in the same pattern as it is on the left hand side, and then I can add it all up and I can double check I've got 4 carbons and 10 hydrogens, so therefore it's C4H10, and that would be 1 mark. Butane burns in oxygen. Complete the word equation to show the complete combustion of butane. So you've got butane plus oxygen. So this is effectively testing you and seeing if you know what you make when you burn a fuel. And the products are the same, whether it's butane or whether it is methane that we might use on a Bunsen burner. Well, oxygen is being reacted, so that means we would make carbon dioxide. And the other gas product that we make, that people often forget about, is water, or specifically water vapour. Question 4.4. Ethene is an alkene. Give a test for alkenes. Give the result if an alkene is present. So the test we use to test whether a substance is an alkane or an alkene is using bromine water. And bromine water is an orange colour. So it starts off orange. Now, if it reacts with an alkene, because it's got that double bond, it will go from orange to colourless. So it reacts and it will then go colourless. If it was an alkane, well, the alkane wouldn't react with it because it doesn't have a double bond. So therefore it will just stay orange because there'd be no reaction. Question 4.5. Each year, many tons of crude oil are extracted from the earth. It took millions of years for crude oil to be formed. What do we call the development that meets the needs of current generations without compromising the resources of future generations? Well, if you're working to get the needs of current without jeopardizing the future, you are being sustainable. Okay, and that's what we are always trying to do in terms of development and products, making it sustainable so we don't ruin the earth for future generations. It's definitely not finite development. Finite means it will run out. Global development and natural development aren't anything. So yeah, it's got to be sustainable. Question number 5 then. Figure 6 shows the percentage by mass of some elements in the Earth's crust. So you've got iron, calcium and magnesium and their percentages. What is the percentage by mass of calcium in the Earth's crust? So we look at calcium, and this is just reading a graph. Well, we can see it's halfway between 3 and 4, so therefore it would just be 3.5%. The percentage by mass of magnesium in the Earth's crust is 2.1%. Draw the bar for magnesium on figure 6. So if we just look at the scale, we see there's 5 squares in between whole numbers. So that means each little square is worth 0.2. So because it's 2.1%, we have to be really accurate with our drawing here. And it would have to be between the one small line between 2.0 and 2.2. Okay, so being really accurate between the little square just above the 2 line. Question 5.3. Copper sulfate is produced during the extraction of copper from the Earth's crust. The copper produced from copper sulfate solution using iron. The word equation for the reaction is copper sulfate plus iron makes iron sulfate plus copper. From the equation, a company calculated that 648 kilograms of copper sulfate are needed to produce 617 grams of iron sulfate and 258 kilograms of copper. Calculate the mass of iron needed to make 258 kilograms of copper. So, when you see numbers written out like this, and it relates to an equation that they normally give you, this is all to do with conservation of mass, which basically means the mass of your reactants equals the mass of your products. So what I think is always best to do is write out the numbers underneath each chemical, so therefore it makes it a bit easier to kind of break down. You've got 648 grams of copper sulfate, so write that underneath it, 648. You've got 617 grams of iron sulfate, 617, and 258 of copper. We are finding out how much iron we have to make up. Now, the rule states of conservation of mass, your reactant mass has to equal your products because you can't lose or gain atoms. So the easiest thing to do would be to add 617 and 258, which would equal 875. So 875 is the mass of your products, and you know that it has to equal the reactants. You know 648 is copper sulfate, so you can minus the 648, and that difference would therefore be your mass of iron that you have to put in, which is 227. And you can just double check it. 648 plus 227 equals 875, which is the mass of those two numbers there. So it works and it's balanced. Question 5.4. Copper is used as a catalyst. Figure 7 shows the reaction profile for a reaction without a catalyst. Draw on an arrow on figure 7 to show the activation energy. So what we need to remember is that on an energy level diagram, the activation energy is the energy needed to start the reaction, and it goes from the base of your reactant line, okay, to the bump, which is the energy we put in. Okay. Figure 5.5, the reaction profile for the reaction without a catalyst is again shown in figure 8. Draw the reaction profile on figure 8 for the same reaction, but this time with a catalyst. So when we draw it with a catalyst, we need to make sure that, remember, the catalyst just speeds up the rate of reaction. It doesn't get involved in the reaction itself. So your reactants and products end up with the same energies. It just makes it happen quicker, and there's less activation energy, okay, because it reduces the amount of energy needed. So it should just look like that because it's reducing the amount of activation energy required. And finally, the last part of this question says, what are catalysts in biological systems called? Well, a biological catalyst, it's not a detergent, that's just a chemical. A polymer is a plastic, so it's not that. A solvent is just a solution, that's not living. So think biological, biology. What topic also came up in biology? Well, it would be enzymes. Enzymes are biological catalysts. Question 6 then. Water that is safe to drink contains dissolved substances. What do we call water that is safe to drink? Desalinated just means no salt. Filtered water, fresh water, or potable. Hopefully we should remember that potable water is our word that we use to describe drinking water. It isn't pure water, but it is still safe to drink. Now, question 6.2 is describe a test for pure water. Give the result of the test if the water is pure. Well, to test the purity of something, we normally test their melting and boiling points. So what we could do is boil the water, okay, and the result would be, if it is pure, it would boil at exactly 100 degrees Celsius. If it was impure, it might mean that it would boil at a lower lower temperature and over a range. For example, 96 to 104 degrees Celsius. The other thing you could do is that instead of testing the boiling point, is testing the melting point. Or you could see if it freezes at 0 degrees exactly. Question 6.3. Describe a method to determine the mass of dissolved solids in a 100 centimetre cubed sample of river water. Okay, so we've got this river water. We want to find out how much dissolved solid is actually on it. So in order to do that, we're going to have to Start off with a beaker of some sort. We're going to add the water into it. We're going to evaporate it away. And then we'll have the salts that are left in it. But what we're also going to need before to do that then is the mass of our container that is empty. Because without that starting mass, we won't be able to figure it out. So it's told us that we've got 100 centimetre cubed of water. So what I would do is I would start off, you get your beaker, let's say we're just doing it in a beaker or evaporating basin, and weigh it empty. So you get your starting reading. You would then add 100 centimetre cubed, because it's told you it has to be 100 centimetre cubed of water. You would then evaporate all water away, and that would leave you with the solid salts at the bottom. And then what you would do is reweigh the evaporating basin. And then finally, to get the actual reading, you would do your final reading minus your starting reading when it was empty. And that would give you the mass of solid. So the mass of the new stuff you've added to it after you've evaporated the water away. Question 6.4. A sample of river water contains 125 milligrams per decimetre of dissolved solids. Calculate a mass of dissolved solids in grams in 250 centimetre cubed of this sample of river water. Give your answer to two significant figures. So this again is an equation that also comes up in chemistry paper 1, but they've carried it through to chemistry paper 2. So the equation is concentration is mass divided by volume. If I put that into a triangle, concentration, mass over volume. So therefore mass is equal to concentration times by volume. So I'm working out my mass. I know my concentration, and it's told me here it's 125 milligrams per decimetre. My volume, though, they've told me is 250 centimetre cubed. I don't want it in centimetre cubed, I want it in decimetre cubed. Remember, there's 1,000 centimetre cubed in 1 decimetre. So therefore, to convert 250 into decimetres, I would divide it by 1,000, and that would give me 0.25 decimetres. So that would give me a reading of 31.25 milligrams, and that is my mass. However, the question isn't asking it for in milligrams, it wants it in grams. So to convert 31.25 milligrams into grams, you would divide it by 1,000, which gives you an answer of 0.03125 grams. But they want it to two significant figures. So therefore, I just want my first two numbers. So it would be 0.31. Question 6.5. A company allows a maximum of 500 milligrams per decimetre cubed of sulfate ions in drinking water. A sample of drinking water contains 44 milligrams per decimetre cubed of sulfate ions. Calculate the percentage of the maximum allowed mass of sulfate ions in the sample of drinking water. Well, you've been told that it's 44 milligrams and they're allowed a total of 500. So you can kind of think of it, I got 44 out of 500, so therefore 44 divided by 500, times it by 100 to put it into a percentage, which gives you an answer of 8.8%. Question number 7 then. This question is about the atmospheric pollutants from fuels. Fuel burns in a car engine. Describe how oxides of nitrogen are produced in a car engine. Okay, so oxides of nitrogen are things like NO2 or NO3. Now, nitrogen and oxygen are both floating about in the air all of the time around us, but they don't react together. They just bounce into each other and keep moving on. They only form compounds together when when combustion happens in a car engine. So why does that happen? Well, when a car ignition actually starts, the temperatures go incredibly high. So there are high temperatures in the engine, and that enables oxygen and nitrogen to react. It's basically giving them enough activation energy to successfully react. Without that high energy, they wouldn't form nitrous oxides. Question 7.2 then. Table 3 shows the carbon footprint during the manufacture and use of 3 cars. It says, evaluate the carbon footprint of the cars, use information in Table 3. So if we have a look at the information that they've given us the mass of CO2 during the manufacture. You've got the mass of CO2 produced when driving per kilometre. You've got the mass of CO2 produced from manufacture and 40 kilometres of driving. And you've got the total mass of CO2 from manufacture and 100 kilometres of driving. So initially, we can see straight away that car A has the lowest mass of CO2 just from making it, and car C has the most. But when you look at the mass of CO2 when driving per kilometre, the mass of car A is the lowest, whereas the mass of car C is actually the lowest. So although car C has more CO2 when it is being made, per kilometre, when it's actually driving and on the road, it's the lowest. So we've got to evaluate the carbon footprint of both of these cars. So basically we need to say which one is best and why, giving advantages and disadvantages of each. So what you could potentially say is start off with one of the cars. So car A has the most mass of CO2 in manufacturing, whereas car C is the least CO2 in manufacturing. Always make sure you put down the obvious mark, never skip it out. Then you can say the next point, car C has the lowest mass per kilometre of driving, whereas car A has the highest CO2 per kilometre. So all I've done here is look at those numbers on the table, and then you can say for both of them, car B is in the middle of both. Car B fits between car A and C for both readings. So the next part we could say could be regarding the total mass of CO2 and manufacture after 100,000 kilometres of driving. And as we can see, car A is actually still got the least amount of CO2 compared to B and C. B is actually in the lead. So that one is potentially the worst. So you could say car B because it fits between car A and C for both readings in terms of manufacturer and CO2 per kilometre, it has the most CO2 released after 100,000 kilometres. And then we can see that A is in the lead, followed by car C. So car A is released the least, followed by car B. However, if it kept on going, and let's say it reached 200,000 kilometres, because car C is producing much less CO2 per kilometre than car A, then eventually car A will overtake car C as being the most amount of CO2. Because eventually, just through driving it more and more per kilometre, it's going to release more. So what I would say to finish it off as my overall conclusion is say, make it clear, because evaluate means give advantages, disadvantages, and then give a conclusion. Overall, car A has the smallest carbon footprint after 100,000 kilometres, but, and emphasise this point, if it reached much further distances, e.g. 200,000 kilometres, car C would then be the most green, or released the least CO2. Okay, now that should bring us to the end of the questions on this paper. So again, there's a copy of the blank paper and mark scheme in the description, along with question by question revision videos for you to go back and look over if you need to. Hope it was useful, and feel free to check out the other walkthroughs if you think it will be useful. Thank you very much.